World Food and Human Population Growth by Russell Hoffenberg, PhD.
Narrated by Russ and Edie Hoffenberg. We all have an awareness that human population growth and the concomitant resource consumption is a problem. Even Drabble has an awareness that there is a problem.
It's a crowded day at the amusement park. I can't tell if we're in Futureland, Wild Westland, or Dinosaur Land.
We're obviously in Futureland.
How can you tell?
They've got a serious overpopulation problem. So, let's look at world population growth. This slide is from the Population Reference Bureau. Of course, the most prominent feature of this figure is the precipitous growth of the human population. To the far right of the figure is one predicted scenario of future population levels. Looking toward the left, the figure indicates that the growth rate began to accelerate about here, at this dotted line, about 10,000 years ago. Looking at the dotted line brings us to another interesting feature of this figure. Look at the scale on the x-axis. It proceeds from the present in 1,000-year decrements. Note the change at the dotted line. The next point to the left of the dotted line is a 1,000,000-year decrement. Let's look at another figure. Again, we see the precipitous growth of the human population. Let's also look again at the scale on the x-axis. From the present, the x-axis proceeds to the left in 1,000-year decrements. From 10,000 years ago, the x-axis jumps to 500,000 years ago. It seems that the point on the x-axis at 10,000 years ago represents something important.
10,000 years ago was the beginning of the agricultural revolution. Because there was certainly plenty of human food available before this time, we are calling the amount of food available before the agricultural revolution the baseline level of food availability. This baseline level of food was available to humans for hundreds of thousands of years, as indicated by the scale on the x-axis. The agricultural revolution was a cultural change which advocates continually increasing human food production. The green and yellow line is the carrying capacity, or the number of people that the amount of available food can support. Again, the green part of the line is baseline human food, and the yellow part is human food production levels.
Let's look at the year 1970. In 1970, the population was 3.7 billion. In this figure, we are showing that globally, the amount of food available could support a much larger global population. In other words, there was more than enough food. In 2002, Renema stated that, quote, "On another plane, evidence coming from such authorized institutions as the FAO, the World Bank, and others have produced facts that are seldom used in the official debates on population. Namely, that at the very moment we are talking about the scarcity of food, enough grain is produced to provide every human being on the planet with 3,600 calories a day. That is enough to make most people fat." This estimate does not even count the many other commonly eaten foods: vegetables, beans, nuts, fruits, grass-fed meats, and fish. End quote. Is there really more than enough food? What if the number of people that the food supply could support was actually equivalent to the number of people that existed in 1970? In other words, if we said that food supply is down here, that in 1970 there was just enough food. This exercise is, in fact, what the Food and Agriculture Organization and the World Bank did. Now, they did this for data analysis purposes. They were not asserting that in 1970 there was just enough food worldwide. But let's see what they came up with.
These data represent approximately 74% of the world population. The squares represent the number of people that food production can support, or carrying capacity, and the diamonds represent population size. Both of these variables are set equal to each other for the year 1970. You can see that food production levels have increased relative to the population even since 1970. These data represent approximately 16% of the world population. You can see a similar trend. These data represent approximately 10% of the world population. The food line is below the population line, but notice that these food data are production numbers. What accounts for the food that supports the population? The answer is, of course, food imports.
For example, this figure shows only net cereal imports in developing countries. Here's the data for sub-Saharan Africa. According to the FAO, cereal imports in developing countries are projected to more than double by 2030. Each region will show significant growth, with the Near East and North Africa continuing to account for the bulk of imports, nearly 40%. Again, globally speaking, there is more than enough food. So, if all of the food production data is taken together, you can see that global food production has more than doubled since 1960, as indicated by the gray line.
We all know that carrying capacity includes water, air, predation and disease, space or habitat, as well as food. The carrying capacity is typically seen as imposing limits to growth or environmental resistance to growth. Note the sigmoidal pattern of population growth in this example.
Ecologists have found that a simple mathematical model encapsulates the pattern of population growth. Kappa is carrying capacity, N is the population, and R is the rate at which the population can potentially grow. Here is the analytic solution to the equation. When carrying capacity is a constant and the population is well below the carrying capacity, the pattern of growth takes the form of a sigmoidal curve. The carrying capacity is typically seen as imposing environmental limits to growth. However, it is important to remember that the carrying capacity also functions as an ecological magnet, drawing population numbers up to it.
Relative to all the other carrying capacity features, human food availability has been and continues to be vastly altered since the beginning of the agricultural revolution. Food is the one carrying capacity variable that has been deliberately and dramatically manipulated. Therefore, kappa, or carrying capacity, or food availability, is not a constant. It clearly has changed over time. In other words, kappa is now a variable.
Because global food production data began to be compiled in the 1960s, I was able to look at the time period from 1961 to 1999 in greater detail. I plotted these data in order to clearly illustrate the carrying capacity impact of food availability on human population. The shape of the figure changed as I plotted these data. This slide will help make sense of the change in the shape of the figure from an almost vertical line to a more horizontal one. These data were compiled by the FAO and the World Bank and represent world food production for the years 1961 to 1999. They set the index equal to 100 for the year 1989. In order to illustrate the carrying capacity impact of the food production index, these data must be converted to carrying capacity, or the number of people that the amount of food can support. First, I shifted the data 1 year forward to account for the time needed for human gestation. This change moves the data 1 point to the right on the x-axis. The 1961 food production index is now the 1962 carrying capacity. Second, the scale on the y-axis was changed to generate a good fit with the actual world population census data for the year 1962. Now that the food production index scale has been converted to a carrying capacity scale, the actual population data can be plotted with the food data, represented here by the red line. Note the similarity to the FAO data that we saw earlier. When the food data is plugged into the logistic equation as a variable kappa, the similarity between actual population numbers and the numbers generated by the logistic equation using food data as a variable carrying capacity illustrates human population growing as a function of increased food availability.
Others have noted that increases in food availability cause human population growth. David Pimentel said, "The populations of all organisms increase to the limit of their food resources." Joel Cohen said, "The ability to produce food allowed human numbers to increase greatly and made it possible eventually for civilizations to arise." Peter Farb said, "Intensification of production to feed an increased population leads to a still greater increase in population." Joel Cohen indicated that human population numbers are a function of or caused by carrying capacity. Russ Hoffenberg indicated that human food production accounts for human carrying capacity and therefore accounts for human population growth. Let's see what Jared Diamond, in his Pulitzer Prize-winning book Guns, Germs, and Steel, has to say about food production and human population. The first connection is the most direct one. Availability of more consumable calories means more people. In short, plant and animal domestication meant much more food and hence much denser human populations. We have seen that large or dense populations arise only under conditions of food production. Agriculture sustains much higher human population densities. Throughout Guns, Germs, and Steel, Diamond consistently links increasing agricultural production with human population growth.
Usually when we get to this point, the issue of per capita food comes to mind. Global per capita food availability, measured as total grains, peaked in 1984 and has been on a steady declining trend. A second-order polynomial regression of the data suggests a steep per capita decline.
However, because population numbers change as a function of carrying capacity, an elevated food supply will precipitate a population increase, leading to per capita food supply numbers that are in dynamic equilibrium with population numbers. In other words, with a food supply that is elevated relative to population, the population will increase and per capita food must eventually decrease. Seen in this light, the per capita food decrease actually provides evidence that food availability or carrying capacity is an ecological magnet that draws population numbers to it. Again, as the population approaches the carrying capacity, per capita food necessarily decreases. It is also important to remember that typically, once a population reaches the asymptote of carrying capacity, population growth approaches zero, and the population stabilizes at a point where there are sufficient resources available.
So how are we increasing food production?
We have increased food production through agricultural expansion.
This figure shows how much habitat is estimated to have been converted primarily through agricultural expansion. According to the Millennium Ecosystem Assessment, humans are fundamentally and to a significant extent irreversibly changing the diversity of life on Earth, and most of these changes represent a loss of biodiversity. The structure and functioning of the world's ecosystems changed more rapidly in the second half of the 20th century than at any time in human history. More land was converted to cropland in the 30 years after 1950 than in the 150 years between 1700 and 1850. Also, cultivated systems now cover 1/4 of the Earth's terrestrial surface. This figure indicates population density. Note that the areas of densest population roughly correspond with the areas of densest agricultural production.
What effects other than causing population growth does agricultural expansion have? Agricultural expansion decreases the ability of the ecosystem to remove carbon dioxide from the atmosphere. Although farmers work to fertilize their crops, converting forest to cropland actually decreases soil nutrients. Available fresh water is diverted to crop production. Species richness decreases due primarily to loss of habitat.
Here we see graphically some of the effects of agricultural expansion just mentioned. Remember that the amount of human food production shown here is at baseline. There is human food here, but not at the production level of cropland. We like to call this shape a healthy cupcake. What does the figure look like after forest is converted to cropland? After forest is converted to cropland, human food production is increased greatly over baseline. However, fresh water is diverted to crop production. Soil nutrients decrease. The ability of the ecosystem to remove carbon dioxide from the atmosphere is decreased, and species richness decreases severely in favor of human food.
Here's another way to look at the problems associated with increases in agricultural production. Agricultural production leads to increases in the human population. Because of the belief that we need to increase food production to feed a growing population, agricultural production is yet again increased, causing a vicious cycle. Other human enterprises which have environmental impact then increase, and these ultimately lead to problems of climate change and loss of biological diversity. The extinction of species and populations is particularly alarming. This is currently occurring at the rate of about 200 species per day. The problem for humans is that this loss of biological diversity chips away at the ecological foundation that supports our lives. In addition to population size, the other variable that interacts to cause our ecological ills is resource use. In 1997, Abernathy wrote, "Perceptions of increasing resource availability encourage and permit high fertility rates. This is followed by a trend of declining fertility as societal expectations for high per capita resource consumption become established and trade-offs between the number of children and resource allocation per person are accepted."
We'd like to take some time to illustrate Abernathy's point. First, there is an inverse relationship between consumption rate and population size for a given carrying capacity or food supply. On the y-axis, we see average per capita resource consumption rate going from frugal to excessive, and on the x-axis, we see population size going from small to large. So, for a carrying capacity here, there can be a maximum population that is very frugal, or a smaller population that is more excessive. As the carrying capacity is increased, the trade-off becomes more pronounced, and even more so with a further increased carrying capacity. Abernathy said that there is a trade-off between resource availability and fertility rates. So we are changing the x-axis to average fertility rate, going from low to high. We are keeping an eye on population size to the right of this figure. When the carrying capacity is low, with a perception that it will be increasing, fertility is at its maximum. Now, is it the general perception that carrying capacity will be increasing? We have already seen evidence from the UN and FAO that this is the case, that the perception is that carrying capacity will be increasing. So as carrying capacity increases, with the perception that it will be increasing further, fertility is at less than maximum, but average resource consumption rates per individual increases, as does the population. With a highly elevated carrying capacity, fertility rates decline much further, and resource consumption increases, as does the population. But note that unless the fertility rate is at or below replacement, the population will continue to grow. Let me repeat what Abernathy wrote. Perceptions of increasing resource availability encourage and permit high fertility rates. This is followed by a trend of declining fertility as societal expectations for high per capita resource consumption become established and trade-offs between the number of children and resource allocation per person are accepted. In order for us to be at this point with a highly elevated carrying capacity, large population size, low fertility rates, and excessive resource use, the Brundtland Report, commissioned by the United Nations, estimated that it would take more than 10 planet Earths to supply the required resources for the population. Another way of illustrating this point is using the classic demographic transition model. This slide is from the Population Reference Bureau and illustrates the classic stages of the demographic transition. In stage 1, both birth rates and death rates are equivalent and high. In stage 2, death rates dramatically decline, but birth rates remain high. In stage 3, birth rates begin to decline, and in stage 4, both birth and death rates are equivalent and low. According to the Population Reference Bureau, women worldwide are having fewer children in their lifetimes, from an average of 5 children born per woman in the 1950s to below 3 in 2000. All of the most recent projections put forth by the UN assume that levels of childbearing will continue to decline in the next century. Birth rates and death rates are declining around the world, but the PRB goes on to say that overall economic development, in other words, resource consumption, public health programs, and improvements in food production and distribution, water and sanitation have led to dramatic declines in death rates, and women now have fewer children than they did in the 1950s. Nevertheless, if death rates are lower than birth rates, populations will still grow. Also, it is possible for absolute numbers of births to increase even when birth rates decline. So, what really happens as the population moves through these demographic transition stages? First, to even be in stage 1, food production must already be at such a high level that birth rate and population size are greatly elevated. With this large population, environmental, medical, and sanitation problems increase the death rate, so that now it matches the birth rate. Once health care and sanitation improve, the population enters stage 2. In stage 2, the birth rate remains elevated and the death rate decreases, so the population naturally increases. As average resource consumption per individual increases, the population enters stage 3. In stage 3 of the demographic transition model, the birth rate declines. As this trend continues, the population theoretically moves to stage 4. In stage 4, birth and death rates are low, but population and resource consumption are highly elevated. Again, in order for us to be at the red X with a highly elevated carrying capacity, low fertility rates, low death rates, and excessive resource use, the Brundtland Report, commissioned by the United Nations, estimated that it would take more than 10 planet Earths to supply the required resources. So, can't we just choose to reduce our world population?
As with other choice behavior, it is best to determine where in the choice process would a desirable outcome be more likely. For example, it may be best to have retirement savings taken out of your pay before you ever receive the check. Although one could save for retirement after receiving the check, success is more likely if the choice is made to have the money withdrawn first. Regarding population dynamics, where in the system is the choice point that will most likely lead to a stable and possibly decreased population? A choice in the process to the left of this figure would make low reproductive rates more probable. As we move the choice point to the right, the probability of success in maintaining a low reproductive rate diminishes, and the reproductive rate becomes higher. So, if we make a choice at the agricultural production stage to halt increases in production, we make it highly likely that reproduction rates will stabilize and diminish. The case of China has shown us that political and economic laws and sanctions help somewhat, but the population will still grow given agricultural increases. Regarding personal choice, for every person that chooses to have one child, resources are then available for someone else to choose to have more children. In theory, it could work that individuals choose to have fewer children even though there is an abundance of food available. It just isn't very likely. And history bears out that, as a global population, given increasing agricultural production, we choose to increase our numbers. Also, we must understand that it is evolutionarily unstable for a population to diminish in a time of abundance.
So far, here's what we know. We know that, globally, there is enough food. We know that making more food, or increasing carrying capacity, makes more people. And we know that in addition to causing population growth, increases in agricultural production cause other ecosystem problems. So why do we do it? Why do we continue to increase human food production?
We do it because we have some very powerful socially maintained beliefs. We believe that other species are subject to the basic ecological law that states that the population of every species increases to the level of its food supply. And we believe that humans are unique and above this basic law. In other words, humans behave as if the human population continues to grow simply because we are human. So it makes sense that humans believe that we need to make more food to feed our growing population.
Let's look at what Heinrichsen, in his seminal work, Winning the Food Race, says about food and human population. This work, written in 1997, is considered by many to be a synthesis of the current beliefs of leading academicians and policymakers. Quote, "In many developing countries, rapid population growth makes it difficult for food production to keep up with demand." End quote. As stated previously, we know that making more food actually makes more people.
Throughout history, societies have raced to keep the food supply equal to or ahead of population growth. Again, we know that making more food actually makes more people. But Heinrichsen seems to contradict himself when he says the global economy probably produces enough food to feed the nearly 6 billion people in the world and even more, if food could be better distributed. More recently, the Millennium Ecosystem Assessment, published in 2005 and commissioned by the United Nations, stated, "On the credit side, 3 of the improving services reflect the worldwide efforts to keep food supply ahead of the increase in population. Total food production increased by about 2.5 times, while the number of people in the world doubled, from 3 billion to 6 billion between 1960 and 2000. In light of the tremendous increase in food production, of course the population would grow from 3 billion to 6 billion. It seems that understanding that human population dynamics are a function of carrying capacity, just as it is with other species, necessitates a paradigm shift, a change in these socially maintained beliefs. It's similar to the paradigm shift that is required to understand that humans evolved here in the same way that all other species evolved. It necessitates thinking outside the box. But some seem to have the following viewpoint.
I'll start thinking outside the box when the box is empty. We are facing a situation in which the box is emptying. Currently, if all species deemed threatened become extinct in the next century, then future extinction rates will be 10 times recent rates. It's not a far logical leap to determine that if human population and resource use continues to grow and we continue to kill off our neighbors in the biological community, one of the many species facing extinction will be the human.
It is our task, first and foremost, to understand the variables underlying our difficulties, that human population growth is caused by increases in food availability. As psychologists, we know that the first step in making a change is to understand and accept what the evidence bears out, that if you keep doing what you're doing, you're going to keep getting what you're getting. If we keep increasing food production, we will be fueling the fire of continued near exponential human population growth and resource consumption. Knowledge and understanding is the key to resolving our difficulties and moving the world towards sustainability.